Everybody, welcome to our Studies webinar today. My name is Martin Besiner, and I'm the president and CTO at Studies. If at some point you'd like to contact me, either usually after the webinar, my personal email is right here, martin@studies.com. And today I'm going to be talking about strategies for sequential experimentation. So this is actually a webinar that I did about 3 or 4 years ago. But since then, we've put in some new stuff into our software that allows this work to be done much easier. So I'm going to show some of that off at the end. So once again, welcome. And why don't we go ahead and get started here. All right, so I'm going to give a quick introduction and kind of motivation to this problem. This is a problem that I've run into quite often when I've been working with people in industry. Textbooks, everything always works out so well. There's never really any run budgets or any other constraints that need to be taken into account, but that's not how the real world works. Then I'll talk about some strategies that you can use for sequential DOE. Then I'm going to go ahead and in PowerPoint go through an example that we have in our mixture design of experiments class. And then kind of the new section this time is a software demo where I'll actually demo our augment design space wizard. And then finally give you some pointers on where you can go if you want more help or if you want to take this work further. So why don't we go ahead and jump right into this. So traditional experimentation, in my experience, I've been at this for over a decade now. It's almost often in textbooks or in webinars, and even in some of the courses we do, taught as a one-shot approach. Okay, meaning you do the experiment and you're done. So a typical example might be something like you choose your factors and you define the low and high value of each one. Could be a mixture component, could be a categorical factor. You use software such as Studies 360 or Design Expert to choose the appropriate experimental design. You take a look at either the power or the precision or the FDS in order to get an idea of how large your design should be so that it has a good chance of giving you the information that you're looking for. Okay, that's this step right here. You go off, you do your experiment, you analyze the data, you optimize, and you figure out kind of where is your optimum, where is the process maximized, where is it minimized, where is it kind of meeting your specifications, and so on. And then oftentimes you might have a run or two, you might do an extra run or two at that optimum, just as kind of a sanity check to make sure you could reproduce what your model is essentially telling you. Okay. So, in my experience, most textbooks, they offer very little or no practical advice on the two steps that I mentioned before. So the first one is computing the expected power or precision of the experimental design, and then adding or subtracting runs needed to achieve the target power or precision. Now, in my experience, experimenters usually, okay, they do not have an unlimited budget of runs. In fact, I mean, I can't think of really an example where somebody wasn't constrained by either money, raw materials, time, any of the things that I had just mentioned. So usually what ends up happening is that people have to settle for power or precision that's a little bit lower than quote unquote what the textbook says, which is usually around 80%. Okay. Now, so what ends up happening, one thing that I've often seen is that people will take their 15 runs, their 20 runs, their 25 runs or whatever. Okay, maybe they're able to get a power of 60 or 70%, and they'll do the experiment and then just kind of go, go with the flow. Whatever the results give them, that's kind of what they end up with. I think that this is a little bit wasteful, okay? And some people are selling themselves short because of this fact that you're doing the experiment in one shot rather than considering, say, a two-part or a three-part experiment. So here is a situation I run into all the time. I mean, this is probably one of the most common, one of the most common sources of disappointment that I see when somebody sends me their design file and they say, "Oh, what could I have done?" Suppose you have just a three-component mixture experiment, so you're blending together three components in various proportions, and you have a run budget of, let's say, 14 runs, so not a huge experiment. And let's say that all of your components can, have a low value of 0.2 and a high value of 0.6, and the total needs to sum up to 1. So an experimenter, following standard advice, okay, is likely going to build a design that looks something like this. Okay, so the gray triangle is this outer gray triangle is the entire mixture space, the 0 to 100% mixture space. And this inner triangle here, sorry about my pen, is kind of not very stable here. This inner triangle is the actual region of experimentation here. Okay, so you could see that there's one run done at each of the vertices, there's 2 runs done in the middle here, and then there's 3 runs done at each of the edges here, halfway along the edges. And this is fine. I mean, this is a perfectly okay design for the experimental design space that has been defined here. Okay. So what's the problem? Well, in theory, there's no problem, because here's what usually the final result of the analysis almost always looks like when you're looking at examples. Now, notice that textbooks or presentations or whatnot, they're always going to choose examples that look like this, where you get this nice, beautiful red region right in the middle. Okay, so you can say my process is minimized or maximized right here in the middle. If I'm looking for maybe a region of operability, maybe I can just choose this little red egg here, and I can operate within that space, and my process should be within its specification. So if this happens, I mean, great. You might be done. Maybe you might do one run here in the middle somewhere later just to kind of confirm. But for the most part, everything looks good. Here's what usually happens, okay? What usually happens is that you end up getting a nice straight plane with this very, very thin red region right along an edge. And in some cases, this actually might be okay, because, even though you're right at an edge, maybe your results are kind of quote unquote good enough here. Okay. But it always begs the question. It says, well, what if my design space had been, this larger triangle out over here? Maybe I could have gotten an even better optimum if I had experimented over there. If I had kind of expanded my range a little bit. Now, I will say that range finding is very difficult. I mean, it's not really a statistical problem, choosing lows and highs. I mean, sure, you can do some preliminary range finding experiments, but it's really a subject matter question. So somebody will ask me sometimes, well, if if I make the low concentration of this reagent, 0.5 or whatever, is that going to be okay? I mean, the question is it really depends on what you know about the subject and maybe historical data and whatnot. Sometimes people will test extremes, but that doesn't really guarantee anything. And it's even more difficult in mixture experiments, because if you want to put in more of one component, well, you kind of have to figure out which components do you want to put in less of, because of the fact that you have this constraint. So it's a very difficult problem. So what now? Well, we had a run budget of 14 runs, and we did a 14 run experiment. And the results show, as I had said, that we may not have fully optimized our process, because the maximum occurs at the edge of the design space. So the question is where do we go now? Well, we had 14 runs and we did a 14 run experiment. Okay, so what do? Do we just accept the results as good enough and move on? I mean, in some cases, that's fine. Some people will say, well, it's close enough to what we were looking for. We don't really need to go any further. Another question is, as well, should we extrapolate? I mean, as you notice, our software and most other softwares, as far as I know, when it builds a predictive model, it typically does not extrapolate beyond the original space, kind of where the points are located. And there's a very good reason for that. Here's something I've seen people do. I've seen people say, hey, you know what? I'm going to throw away this data, throw away the results of this 14 run experiment. I'm going to start over. I'm going to try experimenting in a larger design space. I mean, in theory, that works technically, but I'll show you a better solution down the road here. So could we have done something else to avoid this situation? Now, for 3 components, 14 runs isn't a huge design. It's not tiny, but it's not huge as well. But the question is could we have done something else? And this is what we're going to be talking about now. So here's an alternative approach. So instead of using the entire run budget to do a one-shot experiment, why not say use 75% of the run budget in the first experiment, and then allocate the remainder of the runs based on kind of what happens in that first pass. Okay, and 75, 25% is kind of arbitrary. I mean, it could be 50-50 if you have lots of runs. It could be 90-10. It really is kind of a judgment call. So in the previous example, what we could have done is we could have, instead of using all 14 runs, maybe we could have done a 10-run experiment to get a sense of what's going on. And then based on what happens with those 10 runs, we could have taken a look at what we want to do with the remaining 4 runs. Now, I realize this is not always logistically possible, but in many cases, this is possible. It is possible to do the 10 runs, take 10 minutes to analyze your data, and then go back and do, the remainder of the runs. So if the optimum occurs along an edge, like it did in that little diagram that I had showed you, what we could do is we could reshape the design space or expand it, keeping the original data, and then allocate the remaining 4 runs to fill the additional space. And here's the other thing. If the optimum occurs inside of the original design space, meaning you get, results that look like they quote unquote should, you can go ahead and just keep doing what you're doing and put the remaining 4 runs back in, within the original design space, do the remaining 4 runs, and everything's going to be okay. So it's one of those things where if everything's looking good, just keep doing what you're doing. So here's maybe what I would have done in this situation. I maybe would have started with a 10-run design. And I bet that if you had, I don't have the power statistics here or the precision or the FDS here with me, but just intuitively, my guess is that this would be pretty decent. 10 runs for 3 components is probably going to be pretty decent. So what I would have done is maybe put in 1 run at the vertices, 2 runs at the edges, and then only done 1 run in the middle. So you're still getting 3 replicates, so you can take a look at lack of fit, at least a very, very crude lack of fit test. But what this does is it allows you to see what's going on, and then if it looks like, hey, something is going on over, maybe we think that based on this data, we should be going in this direction. What you can do is you can expand the space out and put the remaining 4 runs over here and possibly get better results. So 2 things can happen in this, let's see here. So as I had showed you, case 1, which is, the more common case, is that you get this red region here, okay, right along the edge there, or you get this happening here, where you get an optimum that occurs kind of in the middle and everything looks good. So case 1, optimum at an edge or vertex. Well, in this case, again, I should have carried over this diagram here, this one here. But in this case, the optimum is obviously along an edge. It's unclear whether this is the true optimum. Maybe if you had gone further out, perhaps the process can be further optimized. And as I had said many times before, perhaps the red region is already good enough and we can stop there. Now, in my experience, and I have seen this quite often, is that many people who are doing experimentation, okay, will either stop because they don't have any more raw materials or they ran out of time or whatever. And you know what I sometimes see is that people will actually think that, okay, this experiment failed, and what they'll do is they'll throw away these runs and basically start over, which is wasteful, but it's not totally unreasonable because this type of strategy of experimentation isn't taught all that often. So they think, okay, it failed, they have to start over. However, in my strategy, we did 10 runs. So we still have a budget of 4 runs left. So is there a way to solve this problem without having to start over or settle for subpar results? And the answer is yes, we can augment the original design space. So we can expand it essentially, and we can perform for the remaining 4 runs within the larger experimental design space. So here is a little demo, kind of an intuitive example. And then we'll go through a real example and also show you how to do this in the software. I'll show you how to do this. So this is one case where, let's say, this blue region, gray region is your operating space, technically anywhere where the process can be run. Blue is your design space. These red dots are the DOE, they're the experiment, and you do the experiment, and boom, right there, that's where your optimum occurs. So your optimum occurs at the edge of the design space, so we can expand the space. So what we do is, okay, so what we do is we look at this picture here. What we do is we basically tell the software, hey, we're going to change the setting for this factor here along this axis and make it go down further. So maybe instead of having a low temperature of 200 degrees, we allow the low temperature to go down to 150 degrees. Okay, so notice how we're keeping all of the data that's in the original blue region. Okay, but now we're adding this green space to try to capture the optimum. After we augment our original design space, our software adds additional runs into the larger design space to try to capture the optimum. The key point here, and I mean, if there's one thing that you take away from this webinar, it's that you don't need to always throw away the original data. Now, there is a caveat here, okay? If it turns out that you do this experiment over here, okay, inside this square, and you totally whiffed, you realize that I'm getting just a totally flat surface there. There's nothing going on. I should have been experimenting in this this region way on the other side of my operating space. Well, in that case, I mean, this data over here might not be all that useful. And yes, you might need to just let it go, set it aside, and start from scratch. But that doesn't happen, in my experience, that doesn't happen all that often, because usually people have some idea of where they should be experimenting, and usually it's just kind of they need to shift over a little bit. It's pretty rare that you have such a situation where your current DOE and your current design space and kind of the design space you should be using is so disjoint. It happens, especially in preliminary experimentation, but usually people have some idea of where they should be to avoid this type of situation. So key points, take-home messages: if we use our entire run budget in the original design space, then we cannot adapt to unexpected results such as optima at the extremes. Keeping some runs in reserve, we can change the shape of the experimental design space as needed. Okay, and you can sequentially expand the space several times as needed. And I know I've talked about augmenting the space, but there are other cases I'll talk about shortly as well. So returning to the mixture example, let's finish this off. And I know this is a pretty simple example. A lot of times you're not going to have an example that's quite this straightforward, but I like to do 3 components or 2 factors just because everything, you can see the picture and you can really kind of catch the intuition here, which is the most important thing, I think. So recall the 10-run mixture example, which had the 14-run total budget, with the following results. So how can we use our software to experiment sequentially? Well, in Design Expert 13, which was some years ago now, you can actually edit the constraints. We used to be really, really strict on not tinkering with the lows and highs because sometimes people were kind of doing dangerous stuff. But this button here appeared in Design Expert 13, and in the following version, we actually had a wizard, which allows this to be done, which I'll show at the end of this presentation. So one thing you can do is you be aware of this, and this is not only in mixtures, this is any design, that has constraints on it, that has RSM factors, mixture components. You can edit these constraints, so you can change them afterwards. So you get something that looks like this. You get this edit constraints dialog, and what you do is you enter the new ranges. So in this case, what I did is A and B, I bumped them up to 0.8, and I allowed C to go all the way down to 0. So that allows me to get more A and B into the mixture, of course, at the expense of how much C is in the mixture, how much of component C is in the mixture. So here's what the expanded design space now looks like in our software. So we have expanded the ranges of 2 components, and we need to add some additional runs to fill the space. So notice how here this blue line here was the original boundary of my space. And now this new white region here, and this is just directly from the evaluation here, this is kind of my new region. But when I do the analysis and I do the optimization, it's still going to take into account all of these runs that I had done over here. So I'm not throwing anything away. Okay, so this is a way to fill the augmented design space. You can augment. You can always add design. You could always add points by augment, design, and augment. And you could actually now, in the wizard, which I'm going to show at the end, I added that at the end, you can actually do the expansion and the point addition in one single step. Okay. So here you can see I'm adding 4 model points. Now the reason why I add 4 model points and not other points is because, well, I really want to get, as much precision as I can. 4 runs isn't a lot. I don't have the luxury of doing a ton of replicates. I already do have replicates in the original space, so I'm just going to choose model points. And here's what the algorithm does is it puts 2 runs here at the vertices, and it puts 1 run here along the middle. So now to finish off, you'll see that the spreadsheet is going to have 4 blank rows, form the additional 4 runs, analyze the data, and re-optimize. One warning here is consider blocking if, for example, you're doing this on a separate day or with a new lot of raw materials, or maybe a different lab tech is doing the additional 4 follow-up runs. You might want to consider blocking, which is the default in our software. So what if everything is okay? I mean, did I screw up? Like, there is always a chance that everything goes okay. And the question is like, if I just did 10 runs and I still have 4 runs left over, did I screw up because I didn't use the 4 runs? I still have them available, but like, what now if everything does work out? Well, first of all, one thing I always like to do is, tell you, look at the confidence interval. Let's say this optimum is somewhere here in this red region. What I always like to do is tell people, look at your confidence intervals, look at your prediction intervals in that region and see how wide they are. Because even if everything looks correct, if you're getting a predicted yield of, let's say, 70% here, plus or minus, let's say 25%, meaning your yield in theory could actually be between 55 and 95%, that might not be great. And maybe what you want is you want a little bit more precision. So the first thing I always do is I always look at the confidence intervals in that region. I see how much precision do I actually have. Okay. So let's say you only do 75% of your run budget and everything goes well, like in the picture that I just showed. So what if you don't need to augment the original design space? The question is how do you allocate the remaining runs in kind of the second step of the sequence? Couple things you can do. Well, first thing is you can allocate the remaining runs in a region around the optimum of the first experiment. Don't allocate the runs as if though you had no prior information. So what you could actually do is, we've been talking about design space augmentation, but you could actually shrink the design space in the second step as well. Okay, so what I can do is maybe I can shrink my space to look, I apologize for that. What you can do is you can shrink the space and you can put the remaining runs in the area of interest to get a little bit more precision where it matters most. Okay, so you don't have to basically just add them haphazardly. You could add them in a more structured way that gives you more information. So adding additional runs near a potential optimum will improve the precision of the designs in the area where it matters the most. So that's basically what I had just said there. So here's what you could do in a second step of a sequence here. The new region, quote unquote, for the remaining 4 additional points, maybe I can shrink the space a little bit, and instead of going from 20 to 60% or zero point 0.2 to zero point 0.6 on each of my components, I can now add the remaining runs in the region 0.25 to zero point 0.5. Maybe I don't need to go all the way out to the vertices here. Okay, of course, you need to choose the new region. In 3 components, it's very easy. In 4 components, it's a little trickier. Okay, and what I typically like to use is the optimization ramps. I like to see, is there one component that's, at its vertex? So here's kind of, 3 different approaches you can look at. Okay, you can say here's our original design, and I'm putting up standard errors here. I'm putting in 4 runs in the original space here. Okay, gives me a standard error of 0.43. And this is at the in the center, I believe, here. And if I add those 4 runs instead in that triangle here, okay, I think it put one at the centroid and it put one at each of those inner vertices, I get a standard error of 0.40 in that region of interest. So I'm doing a little bit better. Okay, it's not an absolutely massive difference, but you could see that in my region of interest, I do get a little bit more precision if I shrink the space for kind of that second step of the experiment. So these are basically just, this is my original experiment here. This is if I had just added 4 runs to the original design space, and this is if I had shrunk the space and added 4 runs to the region of interest. So those are the three things there. Okay. So with that, let me see here. I'm going to actually go through an example that we have in our mixture DOE class, and then I'm going to do a quick demo in Statis 360, and you could also do this in Design Expert as well. Just kind of, showing off the new feature, how to use it, where is it, and so on. But this example, I want to go through because this is a much more sophisticated example. It's more complicated. It's many more components. The pictures don't tell the full story. You kind of have to, it's a real example here. So this is an actual 7-component mixture experiment formulating sunscreen. And what they were trying to do is they were trying to formulate an SPF 40 sunscreen, sun protection factor 40, and an SPF 70 sunscreen. So they actually wanted, as far as I remember, this example is they're blending together a bunch of different sunscreens, and using the same model, they want to try to predict what formulation will give me a 40, what formulation will give me a 70. Now, 3 components along with water were varied. So this is really a 4-component mixture. So once you go to 4 components, you can't really see everything on a single triangular graph. 3 components were held fixed, so these were invariant. Okay, so here is essentially our 4-component mixture design. Totals up to 77 weight percent, so 23 weight percent is held fixed, 77 weight percent is varied. And you can see that most of it's going to be water. So the overall run budget was 30 sunscreen formulations. But what they did here is they only did 20 of them in the first pass of the experiment. So they basically did the minimum number of model points, which is 10, and then they added the 5 lack of fit points and 5 replicate points. They figured, well, we have a run budget of 30, but 20 is kind of a good starting point, so why not start there and see what happens? Okay. So after the experiment was performed, the model was optimized to find the formulation that achieves an SPF 40. Okay. So what they did is, and I'm skipping a bunch of steps here for the sake of time. I'm not going to show the data set and the model building. But once they built their model, they went into the optimization and they tried to target 40. Okay. And now it's not quite, looking at graphs isn't quite as nice because of the fact that you have 4 components. So you could look at 3 components at the same time, and then you have a slider for the 4th, which is kind of a pain. So what I like to do is I like to use the optimization ramps here. And you could see that they could get an SPF of 40 at component A of 1.93, component B 6.48, component C 1.76, and water of 68.1%. So you could see that all 4 of the mixture components were between their lows and highs. There was nothing at its low, nothing at its high. So everything works out. But now the problem is that they also wanted to, with the same experiment, see if they can get a higher SPF formulation of 70. So can the data collected under this design also produce a sunscreen that has an SPF of 70? So here's what they did. They added another goal. They said target of 70 using a lower and upper limit of 45 and 90. And the answer is no. Okay, they can only go up to, looks like 48 here. Yeah, we can only go up about as high as 48. And you could see that component A is almost at its high, not quite there. B is completely at its high. C is completely at its high. And water is at its low. So in this case, I could see that maybe if I had redone this experiment, I should have had B go out further. I should have had C go out further because they're already maximized. So maybe we should put in even more. And obviously that means I have to be willing to put in less water or less of component A, but that doesn't look like it makes sense. So here's what they did. They expanded the space. This is an expansion problem here. And what they did is they changed the limit here. Here are the original limits. Okay, so A now goes up to 3. B originally went from 5 to 10, but they changed it to go from 5 to 15. C originally went from 1 to 2, and they changed it to go from 1 to 3. And water, typically, in this case, since water is almost kind of acts like a filler component, and it's the last component, I just set that to 0, and I let the software figure out kind of like what the lower limit of water has to be. Okay, so it doesn't really matter. It's going to adjust it to make the constraints work out. So augment the design, okay, using this augment design feature here. And here is the actual result. So this is actual real data here. Okay, you could see that 3 of the components were fixed. Those are the gray components. The 4 components that varied were 1, 2, 3, and 6 here. And you could see that this block here was the original DOE. And a second block of runs was added. And you can now see that these yellow highlighted points are components that take at least, those are the runs where at least one component is in its new expanded region. So you can see, for example, run number 22 has 3 yellow highlighted components. That means all 3 of those are in the new region. Okay, component B, run 21. These components here are, and water was not highlighted here, but obviously water is also going to go below its original region as well. So you can see that in run number 21, the second component goes into its new region. So what they did is they reanalyzed, they did the second block of runs, they reanalyzed, and they re-optimized. So you can see now that obviously they can still make an SPF 40 sunscreen because, I mean, it'd be pretty rare for that to fail now, since in the original space they were able to do that. So hopefully in the bigger space that still holds true, and it does. They can also now achieve an SPF formulation of 70 with only 7 additional runs. So you can see that it looked like component A is now, at 2, which was maximized, in the first pass through. Component B needed to go up to 12.86. Its original high was about 10. Component C, the original high was 2, and it needs to go up to 2.9, and then water's at 59%, and they can hit an SPF of right around 70. Okay. So this is a real life example of where they did this with a 4-component mixture example, and they saved quite a bit of time by doing this sequentially, rather than say, okay, restarting from the beginning. Okay, so now with that, I'm going to just do a quick software demo and then just talk about some kind of further topics in the conclusion. Now, I know it's a conclusion, but the conclusion actually has some strategies in there as well for you, so do stick around through the end of that. So I'm going to open up the latest version here of States 360. Let me just make sure it's showing here. So what I'm going to do is I'm going to open up example here. So this is just a very simple example here. It's a 2-factor RSM experiment. And what I want to show you is I want to show you how to use our wizard to augment the space. Okay. I know I'm not going to go through all the analysis and whatnot, the results, because we do that in pretty much every webinar. This is mostly focused on just setting up the design. But the moral of the story here is that when I ran the data, when I looked at the data, I'm going to go to the contour plot, and what it looks like is it looks like I'm getting a maximum that occurs along an edge, kind of in this region here. So it looks like it's occurring. It looks like possibly factor B should have been pushed out a little bit more. Okay, maybe B should have gone up to 1.5, maybe it should have gone up to 2. And in my reach, and if I'm going to do a follow-up experiment here, maybe I don't need to do any runs where B is close to its low. Now let me just kind of explain something here. When you add runs using optimal design, it's going to add the runs in a way that gives the best predictions throughout the whole space, meaning the original space plus the space that you had added. So sometimes you might get some runs that might be back in the original space. If you don't want that, then you have to expand it to be disjoint. Okay, where you have to basically say, hey, my new region is going to be out over here. What I like to do is I like to shift the region over. Okay, so I'm going to show you how to do that. So clearly it looks like B needs to be pushed out a little bit more. Okay, and I'm actually going to show our custom graphs here. This is what the design space looks like. You could see that red is that high point, and blue is where the response is lower. So it looks like there's a region of interest here. And here's how you can do this in our software. What you can do is you can go to Design Tools, Augment Design, and you have Modify Design Space now. Okay, this was not in the previous presentation, so I'm just going to show you. You could basically shrink the space. It actually kind of goes through and shows you a nice little picture here, where here you're shrinking the space, here you're expanding the space, and in this third picture here, you are shifting the space over. Okay, you can also add constraints, meaning if you want to chop off part like a corner, for example, you can go ahead and click on this I want to add constraints button. If you want to modify a constraint, I've only talked about lows and highs, but remember there is a case where people put in linear constraints as well. So what I'm going to do is I'm going to click next, and what I'll do is I'll say my B, I'm going to change the new low. I don't want to go all the way out. I don't want to risk getting any runs all the way out at near -1, so I'm going to change the new low to be 0.5, and I'm going to choose the new high to be 2. So basically what I'm doing is I'm shifting here. Okay. If I really wanted to, I could change this to be 1 and 2, and that's going to only put runs in my new region. Okay, but I don't mind. It basically what ends up happening is that mathematically you have to put in 1 run in the original space when you do a follow-up, especially if you have blocking. Okay, so I'm going to click next here, and what you do is you get this screen that we all know and love here. Typically what I like to do is it's going to put the new runs in a new block by default. I like to typically go with mostly model points, let's say, for example, you only had 4 runs you can do. In that case, maybe I would just add model points. If you can add some, if you had maybe a budget of 6 runs, you can do 1 replicate and you can add 1 lack of fit point and so on. So I'm just going to show a case where we can maybe add 7 runs, okay, and show you what this looks like. I'm going to go ahead and click finish, and I get something that looks like this here. And if I go to the custom graphs here, what I can do is I can put factor B here. Sorry, this goes here, and I'm going to color this by block. And you can see that the green ones are where I have are the new runs that were added, and the red run was the original DOE here. Now you can see that, for example, you might get a point here that might be a little strange. Likely that's a lack of fit point, okay? Which is why I don't love adding lack of fit points when I'm augmenting, but this is, and then there's the replicate that was done here. It was done along that, along that region here. And then what I would do is I would just simply go back, do these runs. I would reanalyze, reoptimize. It's going to use all of the data here. Okay, it's not going to throw anything away, and then call it a day. So it's under Design Tools, Augment Design, Modify Design Space. If you don't like what it's doing here, you could simply delete these runs, okay, and you can try augmenting again if you don't like the way that it looks. Sometimes there is an art to this as well, okay, because intuition and kind of mathematical optimality don't always go hand in hand. So just to kind of conclude here, so here are some benefits of sequential experimentation. So it allows for simultaneous exploration of the design space while also maximizing the information that each run gives you. You're essentially not wasting any runs. You avoid situations where you're stuck with suboptimal results and have no budget left for further experimentation. It can increase the precision in regions of high interest. And in my experiments, there's actually very little research that's done in this area of DOE, and many experimenters aren't even aware of this approach. Or maybe they do it in a very ad hoc manner, which is still fine, I guess. It's better than nothing. Most of the time, people, when they see sequential experimentation, what they think about is screening, augmenting to increase the model order. So what that means is that they keep the same design space, but they add runs to go from, say, a linear to a quadratic model, quadratic to cubic, and so on. Also adding and dropping factors as well. Those are kind of forms of design of sequential experimentation that I think have been pretty well covered, have been well studied. Okay. And of course, there are some caveats. I mean, everything I showed you here looks nice. The pictures came out nice, but it assumes, first of all, that you can even change the lows and highs of your factors without great difficulty. If there's, some machine you need to set up, or there's some, logistical considerations, you might not be able to do this. Okay, or if you have to do all the experiments in a single pass, you might not be able to do this. Okay, so the other thing is if you whiff and your original design space is way, way, way far away from where you should be, this also might not work. So some take-home points. The major point of this webinar is to just, even if the only thing you do is you start thinking about DOE potentially as something you could do in 2 parts or 3 parts or whatever, not a single shot experiment, okay, I think I'd consider that a success. So even just being aware of this technique can be a huge advantage. Generally, in my experience, and this is not scientific, this is not mathematically rigorous, but starting with 60 to almost 80% of your run budget if possible, if the numbers work out. Okay, if there are issues with the experiment, then you can use the remaining 20, 30% in the newly reshaped region, and then the remaining runs can be allocated however you want. If there are no issues with the experiment, you can just simply keep doing what you're doing and put the remaining runs in the original space. So our software allows for factor and mixture component ranges to be changed after design has been created. It also includes a design space augment wizard, which I showed you, that guides you through the entire process. And I could spend probably an hour just going through that wizard, okay, which I might do in a future webinar if there's demand. But hopefully now you're aware of it and maybe you could put it to use at some point. So I want to thank everybody for attending today. Here's my email. It's martin@states.com. If you have any questions, if you have any feedback, I'd be happy to take a look. So I want to thank everybody for joining, And hopefully this was useful to you, and hopefully, it saves you some time or money or whatever in the future. So wish everybody a good morning, a good afternoon, good evening, wherever you are, and take care now. Bye bye.